Welcome to Still Science Lab. Tonight, we are peeling back the layers of red dust and cinematic ambition to confront a harsh, undeniable scientific reality: why Mars is not a place humans can actually live. For decades, pop culture, billionaire visionaries, and even space agencies have painted a picture of a second home for humanity, a rust-colored frontier waiting for our footprints and our glass domes. But the deeper we look into the physics and biology of the red planet, the more we realize that our dreams of colonization are clashing with the brutal laws of the universe. In this investigation, we are stripping away the science fiction to understand the fundamental obstacles that make Mars a lethal environment for the human form. Tonight's journey begins with the most pervasive and inescapable threat of all, a danger that doesn't just surround you, but penetrates you at the molecular level. This is Part 1, The Invisible Killer, focusing on the total absence of a planetary magnetosphere and the lethal cosmic radiation that follows. When we stand on the surface of the Earth, we exist at the bottom of a deep, protective well. We rarely acknowledge the massive, invisible shield that wraps around our planet. But it is the singular reason complex life exists here at all. Deep within the Earth, a molten iron core spins like a colossal generator, creating a powerful magnetic field known as the magnetosphere. This field acts as a planetary deflector, pushing aside the relentless stream of high-energy particles that the Sun and the wider galaxy fire at us every second. On Mars, however, this shield is dead. Billions of years ago, because Mars is much smaller than Earth, its internal heat dissipated. The geodynamo at its center ground to a halt, and its magnetic field withered away. Today, Mars is a naked planet. When you stand on the Martian surface, you are stepping out of the shadows and directly into a crossfire of ionizing radiation that the human body was never designed to endure. This is not a challenge that can be solved with a better spacesuit or a thicker coat of paint. It is a fundamental mismatch between human biology and the raw energy of deep space. The primary source of this invisible fire is the Sun itself. While the Sun provides the light and heat necessary for life, it is also a chaotic nuclear furnace that constantly ejects the solar wind, a stream of protons and electrons moving at millions of miles per hour. On Earth, these particles are trapped and diverted by our magnetic field, creating the beautiful auroras at the poles. On Mars, they strike the surface directly, slowly stripping away the remaining atmosphere and bathing the ground in a constant bombardment. But even more terrifying are solar particle events' sudden, violent bursts of high-energy radiation from solar flares. Without a magnetosphere to deflect these bursts, a single major solar event could deliver a lethal dose of radiation to an astronaut in a matter of hours. There is no warning. And on the barren plains of Mars, there is nowhere to hide unless you are buried deep underground. The surface of the red planet is, for all intents and purposes, a nuclear hot zone that never cools down. Beyond the Sun lies an even more insidious threat: galactic cosmic rays, or GCRs. These are not merely rays of light, but heavy atomic nuclei, stripped of their electrons and accelerated to near-light speeds by distant supernovae. They possess so much kinetic energy that they are essentially unstoppable. Unlike solar radiation, which can be partially blocked by heavy shielding, GCRs are so powerful that they can tear through the hull of a spacecraft or a habitat module like microscopic bullets. In fact, the most dangerous part of GCRs is what happens when they hit something. When a high-energy cosmic ray strikes a metal wall or even a human bone, It creates a spallation effect, a secondary shower of neutrons and radioactive debris that scatters in all directions. Paradoxically, placing a thin shield between a human and a cosmic ray can actually make the radiation dose worse. As the primary particle shatters into a cloud of secondary radiation that is more easily absorbed by human tissue. To truly protect a human from these cosmic bullets, you would need meters of lead or water, or several feet of Martian soil, turning every Martian home into a windowless, subterranean bunker. The biological toll of this constant exposure is catastrophic. Radiation is ionizing, meaning it has enough energy to knock electrons off atoms and break chemical bonds. When these particles strike a human body, they act like a shotgun blast to our DNA. Specifically, they cause double-strand breaks in the genetic code, the most difficult type of damage for our cells to repair. While our bodies are constantly repairing minor DNA damage from terrestrial sources, the sheer volume and energy of Martian radiation overwhelm these natural repair mechanisms. Over time, the cumulative damage leads to a massive spike in the probability of aggressive cancers, particularly in the lungs, blood, and digestive tract. But cancer is only the long-term concern. Recent research suggests that chronic exposure to deep space radiation has a devastating effect on the central nervous system. This space dementia manifests as cognitive decline, memory loss, and a reduction in motor function. For a crew of explorers who must maintain peak mental performance to survive a hostile world, the slow degradation of their brain tissue is a terrifying prospect. Furthermore, we must consider the impact on the technology that keeps us alive. Modern electronics, with their microscopic circuits, are incredibly sensitive to high-energy particles. A single cosmic ray hitting a memory chip can cause a bit flip, a single event upset that can crash a navigation computer or a life support system at a critical moment. Protecting the machines is almost as difficult as protecting the people, requiring specialized, heavy, and expensive radiation-hardened components. The weight of this necessary shielding creates a logistical nightmare. Every kilogram of lead or hydrogen-rich plastic used for shielding is a kilogram of food, water, or oxygen that cannot be carried on the mission. This is the paradox of Mars. The very things we need to survive the journey and the destination are too heavy to launch with current technology. We are trying to carry a piece of the Earth's protection with us, but the Earth's protection is a planetary-scale phenomenon that cannot be packed into a rocket. The lack of a magnetosphere also has a profound effect on the planet's atmosphere, which we will explore in later parts, but its immediate impact is the sterilization of the surface. Mars is not just a place where it is hard to live. It is a place where the environment is actively trying to disassemble the chemical structures that make life possible. Even if we could solve the problems of food, water, and air, the radiation remains a silent, invisible sentinel that makes the surface a death trap. Until we can engineer a planetary-scale, artificial magnetic field, a feat of technology that is currently firmly in the realm of science fiction, the radiation environment of Mars will remain the most significant no-go factor for long-term human habitation. We are creatures of the magnetosphere, evolved to thrive in a protected garden, and the raw, unshielded reality of Mars is a furnace that we are simply not built to survive. As we conclude this first chapter of our investigation, the image of Mars as a welcoming second home begins to fade, replaced by the reality of a world under constant cosmic bombardment. The invisible killer is always there, waiting in the pale pink sky and the red dust, making every second spent on the surface a gamble with cellular integrity. But radiation is only the beginning of the story. Even if we could build a perfect shield, we would still have to face an environment that lacks the very basic fluid of life: air. In the next part, we will look up at that thin, alien sky and understand why the Martian atmosphere is less of a protective blanket and more of a suffocating void. Moving from the invisible fire of cosmic radiation that rains down from the heavens, we must confront a second, equally insurmountable wall that stands between humanity and the red planet: the very air that surrounds it. When we look at the hauntingly beautiful images captured by rovers like Curiosity or Perseverance, it is easy to fall into a sense of false familiarity. We see a pale salmon sky, wispy clouds drifting across the horizon, and dust devils dancing across the plains, all of which suggest a world enveloped in a gas-filled embrace similar to our own. But this is a lethal optical illusion. The Martian atmosphere is not a protective blanket. It is a whisper of gas, so thin and so chemically hostile that it defies almost every requirement for human biological survival. To step onto Mars without the protection of a pressurized suit is not merely to step into a place with thin air, but to step into a functional vacuum that would reclaim your life in a matter of heartbeats. In this second chapter of our investigation, we move from the radiation of the heavens to the suffocating reality of the Martian sky, exploring why the air on Mars is effectively an atmosphere of nothing. To truly grasp the scale of this atmospheric poverty, one must look at the sheer numbers that define the Martian environment. On Earth, we exist at the bottom of a heavy, life-sustaining ocean of gas that exerts a pressure of approximately 101.3 kilopascals at sea level. This pressure is what keeps our lungs inflated, our liquids stable, and our bodies held together. On Mars, the average surface pressure is a staggering 0.6 kilopascals. This means the Martian atmosphere is roughly 1% as thick as Earth's. To find air this thin on our home planet, you would have to ascend to an altitude of over 30 kilometers, 3 times the cruising altitude of a commercial airliner and far above the peak of Mount Everest. Even at the highest point on Earth, in the legendary death zone, where elite climbers must use bottled oxygen to prevent their organs from shutting down, the air is still a dense, rich soup compared to the void-like conditions of the Martian surface. On Mars, there is no death zone to enter because the entire planet is a death zone. The chemical composition of this thin veil is the next terrifying hurdle. Earth's atmosphere is a finely tuned mixture of approximately 78% nitrogen and 21% oxygen, providing the stable chemical buffer our respiratory systems evolved to process. Mars, by contrast, is a world dominated by carbon dioxide. Approximately 95% of the Martian atmosphere consists of CO2. While science fiction often suggests that we could simply use plants to turn this into oxygen, the reality for a human explorer is far more immediate and violent. Carbon dioxide in such high concentrations is not merely an inert gas that displaces oxygen. It is a potent metabolic poison. On Earth, even a slight increase in CO2 levels in an enclosed space leads to headaches, confusion, and dizziness. At Martian concentrations, it causes rapid hypercapnia, a condition where the blood becomes dangerously acidic, leading to respiratory failure, seizures, coma, and death within minutes. There is no possibility of breathing easy on the red planet. Even if the atmospheric pressure were somehow magically raised to Earth-like levels, the air would remain a toxic gas that would need to be entirely scrubbed and replaced before a human could take a single, unassisted breath. The reason for this atmospheric desolation is a direct consequence of the tragedy we explored in our first part. Because Mars lost its global magnetic field billions of years ago, it lost its ability to defend its atmosphere against the solar wind. Without a magnetosphere to deflect high-energy particles, the Sun has spent eons sandblasting the Martian exosphere. This process, known as atmospheric stripping, occurs when solar particles strike gas molecules with enough force to give them the kinetic energy needed to escape into deep space. Observations from the MAVEN spacecraft have confirmed that Mars is literally leaking into the void, losing roughly 100 grams of its atmosphere every second to the solar wind. Over millions of years, this relentless erosion has turned what might have once been a thick, watery world into the desiccated husk we see today. Mars is a planet that has been bled dry of its volatiles, leaving behind only the most stubborn traces of gas, incapable of providing the thermal or physical protection required for complex life. One of the most profound consequences of this atmosphere of nothing is the total loss of planetary temperature regulation. On Earth, our thick atmosphere acts as a thermal flywheel, trapping solar heat through the greenhouse effect and distributing it across the globe through complex wind and current patterns. Mars has no such insulation. Because the air is so sparse, it has almost no heat capacity. This means that even if you were standing at the Martian equator at noon on a summer day and felt a relatively comfortable 20 degrees Celsius at your feet, the air at the level of your head would be below freezing. As soon as the sun dips below the horizon, there is nothing to hold the heat in. The temperature plummets instantly, often reaching negative 73 degrees Celsius or lower in a single night. For a human colonist, this means survival is a constant, high-energy battle against the cold. Every habitat, every suit, and every vehicle must be a masterpiece of insulation, requiring massive amounts of power just to prevent the occupants from becoming frozen statues in a matter of hours. The lack of density also creates a sensory experience that is eerie and alien, specifically regarding the behavior of sound. On Earth, sound is the vibration of air molecules, and our thick atmosphere carries those vibrations efficiently over long distances. On Mars, sound behaves in a fractured, muted way. Because the air is so thin and composed primarily of carbon dioxide, it absorbs high-frequency sounds almost immediately. The chirp of a mechanical sensor or the whistle of a teammate would disappear over a distance of only a few meters. Only low-frequency rumbles can travel any significant distance, and even then, the speed of sound is slower than it is on Earth. If you were to stand on Mars without a helmet and shout to someone standing just 10 feet away, your voice would sound faint, muffled, and distorted, as if you were speaking through several layers of thick wool. The Red Planet is a world of acoustic isolation, a place where the silence is heavy and the air refuses to carry the signals of life. The engineering challenges posed by this thin air are perhaps best understood through the Mars landing problem. On Earth, we use the atmosphere to our advantage when returning from space, utilizing heat shields to shed velocity and parachutes to drift gently to the ground. On Mars, the air is in a Goldilocks zone of uselessness. It is thick enough to generate immense, destructive heat during entry, but too thin to provide enough aerodynamic drag for a parachute to slow down a heavy human-rated payload. Every landing on Mars is a high-stakes, terrifyingly fast descent that requires complex retro-rockets or sky cranes to prevent the spacecraft from becoming a new crater. We cannot rely on the air to help us land. yet we must fight through its friction to reach the surface. This makes the delivery of the tons of life support equipment, food, and water required for human survival an incredibly risky and astronomically expensive endeavor. Even the concept of living off the land by extracting oxygen from the carbon dioxide is a monumental industrial task. While experiments like MOXIE have proven we can chemically split Martian carbon dioxide into oxygen, the scale required to support a living, breathing human is staggering. To survive, a crew would need industrial-scale oxygen plants running around the clock, consuming vast amounts of energy in an environment where power is already at a premium. Furthermore, any habitat built on Mars must be designed as a high-pressure vessel, more akin to a submarine or a space station than a traditional building. The pressure differential between the inside of a base and the Martian outside is so extreme that every seam, every seal, and every airlock is a potential point of catastrophic failure. A small crack wouldn't just result in a draft. It would lead to explosive decompression, killing everyone inside in an instant. As we stand on the metaphorical plains of the red planet, looking up at that thin, salmon-colored sky, we must realize that we are looking at a vacuum that is actively hostile to our existence. The Martian atmosphere is not a resource. It is a barrier that refuses to let us breathe, refuses to keep us warm, and refuses to protect us from the void. It is a world where the air itself is an enemy. But as dangerous as the chemistry and density of the air are, there is a more visceral, terrifying physical threshold we have yet to cross. In our next chapter, we will look at what happens to the human body itself when subjected to these low pressures. We will explore the Armstrong Limit and why, on the surface of Mars, your very blood becomes a boiling threat to your life. While our previous explorations into the cosmic radiation and the thin, toxic atmosphere of Mars have already painted a grim picture of survival, we have yet to discuss the most visceral and immediate threat to the human form: the physical integrity of your body itself. In science fiction, we often see characters dashing across the Martian surface with nothing but a thin mask, or perhaps holding their breath for a quick sprint. In reality, the physics of the red planet would make such a feat impossible, not because of a lack of oxygen, but because of the fundamental relationship between atmospheric pressure and the boiling point of liquids. On Earth, we are used to the idea that water boils at 100 degrees Celsius, but this is only true because of the weight of the air pressing down on us at sea level. As pressure drops, so does the temperature required for a liquid to turn into a gas. On Mars, where the pressure is less than 1% of Earth's, we encounter a terrifying physiological threshold known as the Armstrong Limit. This is the point where the boiling point of water drops to 37 degrees Celsius, the exact internal temperature of the human body. This means that on the surface of Mars, without a pressurized environment, your very life fluids would begin to boil away into vapor while you are still alive. To understand the horror of the Armstrong Limit, we must first look at the basic physics of phase transitions. A liquid stays a liquid because atmospheric pressure acts like a lid, holding the molecules together. When you remove that lid, the molecules can escape into a gaseous state with very little energy. On Earth, the Armstrong Limit occurs at an altitude of approximately 19 kilometers. If a pilot's cockpit depressurizes at this height, they face immediate and catastrophic physical consequences. On Mars, the entire surface is well above this limit. This creates a scenario where the moisture on your tongue, the tears in your eyes, and the delicate linings of your lungs would instantly begin to transition from liquid to gas. It is a common misconception, fueled by Hollywood, that a human exposed to a vacuum would explode or instantly freeze solid. The reality is more subtle, but equally lethal. Your skin is actually strong enough to prevent your blood from literally boiling inside your veins. The elastic tension of your circulatory system provides just enough internal pressure to keep your blood liquid for a short time. But the mucous membranes and the soft tissues of the body have no such protection. The most immediate and critical failure happens in the lungs. We are accustomed to thinking of our lungs as organs that pull oxygen out of the air and into our blood. However, gas exchange is a two-way street governed by partial pressures. In the near vacuum of Mars, the concentration of oxygen in the atmosphere is essentially zero. Because the pressure outside is so much lower than the pressure inside your blood, the process of respiration reverses. Instead of oxygen moving from your lungs into your bloodstream, the oxygen already in your blood is violently sucked out into your lungs and exhaled into the Martian void. This leads to a condition called fulminating anoxia. You wouldn't just be holding your breath, you would be actively deoxygenating your own brain with every passing second. Within roughly 15 seconds, your brain would be starved of oxygen, leading to a total loss of useful consciousness. You would collapse long before you felt the urge to gasp for air, essentially becoming a passenger in your own dying body. While your brain is shutting down, a phenomenon called ebullition begins to take hold in your tissues. This is the formation of gas bubbles in the soft tissues and the smaller blood vessels. As the water in your cells begins to vaporize, your body would begin to swell. You wouldn't pop like a balloon, but you would expand to perhaps twice your normal size as the steam pockets grow beneath your skin. This swelling would be particularly visible in the extremities and the face, causing profound internal bruising and tissue damage. If you were somehow rescued and repressurized within a minute or two, you might survive, but you would be covered in ruptured capillaries and suffering from a systemic case of the bends, as nitrogen and other gases bubble out of your blood, blocking blood flow to your vital organs and causing agonizing joint pain. This physiological reality dictates every aspect of Martian exploration technology. A spacesuit on Mars is not just a suit, it is a human-shaped spacecraft. To keep an astronaut alive, the suit must maintain a constant internal pressure of at least 30 to 40 kilopascals, usually using pure oxygen to compensate for the lower overall pressure. However, this creates a secondary engineering nightmare. The suit becomes a rigid, overinflated balloon. Imagine trying to bend a fully pressurized fire hose. That is what it feels like for an astronaut to move their arms or legs in a standard EVA suit. Every movement requires immense physical effort against the internal pressure of the suit, leading to rapid exhaustion and the risk of repetitive strain injuries. This is why you see astronauts moving with a strange, stiff-legged gait. They are literally fighting the physics of their own life support system. The pressure differential also makes the threat of a leak a constant psychological burden. On Earth, a small hole in a tire or a tent is a minor inconvenience. On Mars, a small tear in a glove or a seal failure in a helmet is a life-threatening emergency. The air doesn't just leak out, it escapes with explosive force. If a suit were to suffer a major breach, the drop in pressure would be so instantaneous that the astronaut would have no time to react. The sudden cooling caused by the rapid expansion of gas, known as adiabatic cooling, would cause the moisture in the mouth and throat to freeze, even as it boils. a paradoxical and excruciating sensation. The transition from a living, thinking explorer to a swollen, unconscious form happens in the time it takes to blink. Furthermore, we must consider the long-term effects of living in these high-pressure habitats surrounded by a low-pressure world. To enter or exit a Martian base, astronauts must use an airlock, a process that can take hours. To prevent the bends, explorers must undergo a pre-breathe period, where they purge the nitrogen from their blood by breathing pure oxygen for an extended time. This makes spontaneous exploration impossible. You cannot simply step outside to see the sunset. Every exit is a choreographed industrial operation. The constant cycle of pressurization and depressurization also puts immense mechanical stress on the habitat itself. Metal fatigues, seals degrade, and the constant breathing of the structure increases the risk of a catastrophic blowout. We are talking about living in a pressure cooker in reverse, where the slightest mechanical failure leads to the Armstrong Limit reclaiming its territory. The boiling point of your own fluids is perhaps the most humbling reminder of how unsuited we are for the red planet. We are creatures of one atmosphere. Our enzymes, our cellular membranes, and our very consciousness are tuned to a specific weight of air that Mars simply cannot provide. We could bring all the oxygen in the world, but without the weight of the atmosphere to hold us together, we are merely a collection of liquids waiting to evaporate. As we move forward in our journey, we will see that even if we stay inside our pressurized bubbles and shield ourselves from the radiation, the very ground beneath our feet is plotting against us. In the next part, we will descend to the Martian surface and look closely at the dust, a substance that isn't just dirt, but a toxic chemical cocktail that makes farming and even breathing a deadly gamble. Even if we could shield ourselves from the rain of cosmic fire, thicken the air to a breathable pressure, and stop our blood from boiling at the Armstrong Limit, the very ground beneath our feet on Mars would still be plotting our demise. In the popular imagination, the red soil of Mars is seen as a vast, untapped resource, a planetary-scale garden waiting for the first pioneers to plant the seeds of a new civilization. We have seen cinematic portrayals of astronauts successfully growing crops in Martian regolith, leading us to believe that with enough water and a bit of fertilizer, the red planet could become a self-sustaining Eden. However, the chemistry of the Martian surface tells a far more sinister story. The iconic rust-red dust that covers every inch of the planet is not just crushed rock. It is a toxic chemical cocktail that makes the prospect of Martian agriculture, and even the simple act of breathing, a deadly gamble. The primary culprit in this environmental minefield is a class of chemicals known as perchlorates. On Earth, perchlorates are relatively rare in nature, found primarily in the hyper-arid Atacama Desert. For us, they are mostly known as industrial waste, or a key component in solid rocket fuel and pyrotechnics. On Mars, however, perchlorates are everywhere. They are spread across the entire planetary surface in concentrations ranging from 0.5% to 1% of the soil's mass. This might seem like a small amount, but in the context of biological systems, it is an overwhelming and lethal dose. Perchlorates are powerful oxidizers, and their presence on Mars is likely the result of eons of ultraviolet radiation interacting with chlorine-rich minerals in the soil. For a human explorer, this means that the very dust they kick up with every footstep is laced with a potent metabolic toxin, The most immediate danger of perchlorates is their impact on the human endocrine system. Perchlorates are competitive inhibitors of iodine uptake in the thyroid gland. The thyroid uses iodine to produce essential hormones that regulate metabolism, heart rate, and body temperature. Because the perchlorate ion is similar in size and charge to an iodine ion, the thyroid mistakes the toxin for the nutrient. If a Martian colonist were to inhale even trace amounts of Martian dust, which is inevitable given the planet's frequent storms and the static nature of the regolith, the perchlorates would enter their bloodstream and begin to starve their thyroid of iodine. Over time, this leads to hypothyroidism, causing profound fatigue, muscle weakness, depression, and cognitive impairment. In a high-stakes environment where survival depends on constant vigilance and physical stamina, a compromised thyroid is not just a medical condition, it is a mission-ending catastrophe. The toxicity of the soil also shatters the dream of living off the land through agriculture. While Martian soil contains many of the minerals plants need, like magnesium and potassium, the perchlorates make it a hostile medium for Earth-based life. At the concentrations found on Mars, perchlorates are toxic to almost all known food crops. To turn Martian regolith into viable soil, colonists would first have to undergo a massive, energy-intensive industrial cleaning process. They would need to wash the soil with massive quantities of water to leach out the salts water that is already at a premium, and then find a way to dispose of the toxic perchlorate-rich brine that remains. This isn't just gardening, it is a complex chemical engineering task that requires heavy machinery, specialized filters, and a constant supply of energy. The idea of a lone astronaut surviving on potatoes grown in raw Martian dirt is, quite simply, a scientific impossibility. Beyond the chemical toxicity, the physical nature of Martian dust is an engineering nightmare. On Earth, dust and sand are rounded by the action of wind and water over millions of years. On Mars, where there is no liquid water and the wind is too thin to provide significant mechanical weathering, the dust particles remain incredibly jagged and angular. They are like microscopic shards of glass. This makes the dust extremely abrasive. It eats through the seals of airlocks, clogs the hinges of mechanical joints, and scratches the visors of spacesuits. Because the Martian environment is incredibly dry and the surface is constantly bombarded by ultraviolet light, the dust also carries a powerful static charge. It clings to everything: suits, boots, equipment, and solar panels with a tenacity that defies simple brushing. This leads to the airlock contamination problem. No matter how careful an astronaut is, they will inevitably bring Martian dust back into their habitat. It sticks to the folds of their suits and the treads of their boots. Once inside the pressurized environment, the dust dries out and becomes airborne, circulating through the habitat's ventilation system. The colonists would find themselves living in a permanent haze of toxic, abrasive microparticles. Inhaling these jagged shards of iron oxide and perchlorates would lead to chronic respiratory inflammation, similar to the lunar hay fever reported by Apollo astronauts, but with the added layer of chemical poisoning. Long-term exposure could lead to silicosis-like scarring of the lungs or Martian lung, a condition that current medical science is entirely unprepared to treat. The chemical reactivity of the soil also poses a threat to the hardware that keeps humans alive. Perchlorates, as strong oxidizers, are highly corrosive. When combined with the slight humidity inside a human habitat or a greenhouse, They can attack metal surfaces, electronic connections, and synthetic fabrics. A Martian colony would be in a state of constant decay, with the environment actively trying to dissolve the very structures meant to protect the inhabitants. The dust would find its way into the most sensitive electronics, causing short circuits or corroding delicate sensors. This means that every piece of equipment on Mars has a drastically shortened lifespan compared to its performance on Earth. Maintenance would be a never-ending cycle of cleaning, repairing, and replacing parts that have been sanded and oxidized by the red grit. Even the water on Mars, trapped as ice in the regolith or the polar caps, is likely tainted. Any attempt to melt and use Martian ice for drinking or irrigation would require sophisticated multi-stage filtration to remove the dissolved perchlorates. The infrastructure needed to provide clean water to a colony would be massive, far beyond the portable filters used by hikers or even the systems used on the International Space Station. We are talking about a world where the ground itself is anti-life, a place where the basic building blocks of a civilization, soil and water, are contaminated at a fundamental chemical level. Furthermore, we must consider the environmental impact of human presence on Mars. If we were to introduce Earth-based bacteria into this perchlorate-rich environment, we run the risk of creating a new, unpredictable chemical cycle. Some Earth microbes can actually breathe perchlorates, breaking them down into chlorine and oxygen. While this sounds like it could be part of a terraforming strategy, the scale required is astronomical, and the side effects, such as the release of massive amounts of chlorine gas, could be just as deadly as the perchlorates themselves. We would be attempting to perform planetary-scale chemistry with a biological system we don't fully understand, in an environment that is already trying to kill us. In the end, the toxic soil of Mars is a reminder that we are not just biological entities, we are chemical ones. Our bodies are tuned to a specific geochemistry that Earth provides and Mars lacks. The red dust is not an invitation, it is a warning. It tells us that this is a world where the basic elements are out of balance with our needs. We can build our bubbles and filter our air, but as long as we are standing on the perchlorate-laden plains of the red planet, we are living on a foundation of poison. As we look out across the dusty, rusted horizon, we begin to realize that the chemical hostility of the ground is only matched by the crushing physical reality of the temperature. In the next part, we will leave the toxic dirt behind and face the absolute cold of the Martian night, a freezing void that turns survival into a desperate, never-ending battle for energy. The transition from the chemical toxicity of the soil to the thermal brutality of the Martian environment is perhaps the most immediate shock to any biological system attempting to survive outside of a laboratory. On Earth, we are cushioned by a thick, moist atmosphere that acts as a planetary heat sink, moving energy from the sun around the globe and keeping the temperature within a relatively narrow, life-friendly band. Even in our coldest deserts or at the peaks of our highest mountains, the air around us retains a certain amount of thermal mass. Mars has no such luxury. Because the atmosphere is a near vacuum, it lacks the ability to store heat or provide insulation. When the sun sets on the red planet, the heat doesn't just dissipate, it vanishes into the vacuum of space with terrifying speed. This is the reality of the freezing void. A world where the average temperature is a bone-chilling -62 degrees Celsius, and where the difference between life and death is a constant, uncompromising supply of electricity. To understand the Martian cold, one must first understand that temperature on Mars does not behave like temperature on Earth. On our home planet, air temperature is relatively consistent from your feet to your head because the thick air is constantly mixing. On Mars, because the air is so thin, there is a massive thermal gradient. A rover standing on the equator at noon might record a pleasant 20 degrees Celsius at its base, while its head sensors just 2 meters higher are experiencing sub-zero temperatures. This means that a human explorer would be standing in a world where their boots are in a summer afternoon and their helmet is in a winter midnight. This creates immense mechanical stress on suits and equipment as different parts of the same object expand and contract at vastly different rates. This thermal whiplash is a constant threat to the structural integrity of every seal, joint, and weld in a Martian colony. While the average temperature of -62 degrees Celsius sounds survivable with the right coat, the reality is far grimmer. In the Martian winter, especially near the poles, temperatures can plummet to -125 degrees Celsius. At these extremes, carbon dioxide actually freezes out of the atmosphere, falling as dry ice snow. This is a level of cold that defies human experience. Even Antarctica, the coldest place on Earth, is a tropical paradise by comparison. In Antarctica, the air is still dense enough to provide some resistance to heat loss. On Mars, you are essentially standing in a cryogenic freezer that is also a vacuum. While the thin air means you don't lose heat through convection as quickly as you would in a cold wind on Earth, you lose it through radiation. Your body, being a warm object, is constantly beaming its heat away into the blackness of space, and there is no atmosphere to reflect that heat back to you. This creates the energy battle, a desperate, never-ending struggle to maintain a thermal equilibrium. In a Martian colony, energy is not a luxury for lighting or computers. It is the primary currency of survival. Every watt of power generated must be carefully partitioned between life support, oxygen production, and, most importantly, heating. The sheer amount of energy required to keep a human-sized habitat at a livable 20 degrees Celsius when the outside environment is at -80 is staggering. If the power grid of a Martian base were to fail for even a few hours, the habitat would cold soak. The internal temperature would drop so rapidly that the inhabitants would succumb to hypothermia long before they ran out of air. Unlike an Earth-based survival situation where you might build a fire or huddle for warmth, on Mars, there is no combustion and no ambient heat to scavenge. You are entirely dependent on the machine. This dependency is complicated by the fact that the cold itself actively destroys the systems meant to provide power. Batteries are perhaps the most vulnerable link in this chain. Most battery chemistries rely on liquid electrolytes that become sluggish or freeze entirely in Martian temperatures. A battery that provides an hour of power on Earth might fail in minutes on Mars, unless it is encased in its own heated, insulated warm box. This creates a paradox. You need energy to keep your energy storage systems warm enough to provide energy. This parasitic power drain eats away at the efficiency of the colony, forcing engineers to build much larger solar arrays or nuclear reactors than would otherwise be necessary. Solar power, the most common proposal for Martian energy, is particularly hampered by the cold and the planet's distance from the Sun. Mars sits roughly 140 million miles from the Sun, receiving only about 43% of the solar energy that reaches Earth. Combine this with the extreme cold, which reduces the efficiency of electrical components, and the frequent dust storms that can block out the sun for months, and you have a recipe for an energy crisis. During a Martian winter or a global dust storm, a solar-powered colony would find itself in a death spiral. As the sun fades, the temperature drops, requiring more heating power, just as the power supply is vanishing. This is not a theoretical risk. It has already claimed the lives of several robotic missions, including the Opportunity rover, which was silenced forever when a dust storm cut off its ability to stay warm. The infrastructure of a colony faces its own set of cold weather demons. Most materials we use for construction, plastics, rubbers, and many metals become incredibly brittle at -60 degrees. A seal that is flexible on Earth can become as fragile as glass on Mars. If a pressurized habitat experiences a sudden impact or even a slight structural shift while cold-soaked, the material could shatter rather than bend, leading to the catastrophic decompression we discussed in Part 3. Lubricants also fail, turning from smooth oils into thick, sticky pastes that seize up gears and motors. Every moving part on Mars, from the wheels of a rover to the hinges of an airlock, must be specially engineered with space-grade heaters or solid-state lubricants that can withstand the freezing void. Psychologically, the cold adds a layer of oppressive isolation. On Earth, we are used to the idea that the outdoors is a place of refreshment. On Mars, the outdoors is a lethal void that will freeze your lungs and boil your blood. The colonists would be confined to their pressurized, heated bubbles for the vast majority of their lives. The knowledge that only a few centimeters of insulation stand between you and a temperature that would freeze your cells solid creates a state of perpetual low-level stress. There is no such thing as a walk in the fresh air. Every exit is a high-risk operation into a world that is fundamentally incompatible with the warmth of human life. Even the process of scientific discovery is hindered by the cold. Water ice, which we need for fuel and drinking, is often frozen into a state called interstitial ice, meaning it is bonded to the soil like concrete. Mining this ice in sub-zero temperatures requires massive amounts of thermal energy to melt it out of the ground, further straining the colony's power budget. We are not just visiting a cold place. We are trying to build a civilization in a world that is permanently at the temperature of liquid nitrogen's cousin. As we look at the frost-covered plains of Mars, we realize that the red planet is not just a desert, it is a cryogenic desert. It is a place where the very concept of warmth is an artificial construct that must be defended every second of every day. The freezing void ensures that any human presence on Mars will be fragile, expensive, and utterly dependent on a continuous flow of energy that the planet itself refuses to provide. But even if we could find a way to stay warm and shield ourselves from the radiation and the toxic dust, there is one more fundamental force that we cannot escape, a force that works on our bodies from the inside out. Every moment we are there. In the next part, we will look at the silent, inescapable influence of gravity and why the lightness of Mars is actually a heavy burden for the human heart, bones, and eyes. The transition from the external threats of radiation, vacuum, and freezing temperatures brings us to a challenge that is perhaps even more insidious, because it is a force that acts on our bodies from the inside out. Every single second of every day on Earth, we are defined by the gravity we live in. Our hearts, our bones, our muscles, and even our very cells have evolved over millions of years to function perfectly under the constant pull of 1G. When we look at Mars, we often see the lighter gravity as a benefit, a world where you could jump 3 times as high, carry heavy loads with ease, and feel a sense of permanent physical liberation. But to the human body, The 38% gravity of Mars is not a gift. It is a slow-motion biological disaster. Gravity is the mechanical signal that tells our bodies how to maintain themselves, and without the full strength of that signal, the human frame begins to unravel. In this 6th chapter of our investigation, we move from the environment to the anatomy, exploring why the lightness of Mars is a heavy burden that leads to systemic physiological decay. The most immediate and well-documented effect of low gravity is the rapid loss of bone density. On Earth, our bones are not static structures. They are living tissue in a constant state of remodeling. Cells called osteoblasts build new bone, while cells called osteoclasts break down old bone. In 1G, the stress of walking, standing, and lifting provides the mechanical feedback that tells the body to keep the bones strong. On Mars, that feedback is largely absent. Because the physical load on the skeletal system is reduced by more than 60%, the body's internal logic decides that maintaining a heavy, dense skeleton is an unnecessary expenditure of energy. The result is a condition similar to an accelerated form of osteoporosis. Astronauts in microgravity lose bone mass at a rate of roughly 1 to 1.5% per month. While Mars has some gravity, it is likely not enough to halt this process. Over a multi-year mission, an explorer's bones would become increasingly porous and brittle. Even a minor fall or a sudden movement could result in a catastrophic fracture that would be nearly impossible to heal in a low-gravity environment where the body is already biased toward bone resorption rather than bone creation. While the bones are turning to glass, the muscular system is undergoing its own form of biological rusting. Muscles that are not required to fight against a full Earth gravity load quickly begin to atrophy. This is particularly dangerous when it comes to the most important muscle in the body, the heart. The human heart is an incredibly efficient pump designed specifically to push blood upward against the pull of Earth's gravity to reach the brain. On Mars, the heart doesn't have to work nearly as hard. Over time, like any muscle that isn't used, the heart muscle begins to shrink and weaken. The chambers of the heart can actually change shape, becoming more spherical and less efficient. This cardiovascular remodeling means that a Martian colonist would possess a heart perfectly tuned for a 38% gravity world, but one that would be utterly incapable of functioning if they ever attempted to return to Earth. To a long-term Martian resident, Earth wouldn't just be heavy. It would be a world where their own heart might fail under the sudden, crushing weight of its original home. The issues with blood don't stop at the heart muscle. In low gravity, the fluids in the human body undergo a dramatic redistribution known as a fluid shift. On Earth, gravity pulls our blood and interstitial fluids toward our lower extremities. On Mars, these fluids migrate upward toward the chest and head. This leads to what astronauts call the puffy face, chicken legs syndrome. While this might sound like a cosmetic issue, the internal reality is much more serious. The brain perceives this influx of fluid as an overall increase in blood volume, triggering the body to shed fluids through the kidneys, leading to chronic dehydration and a reduction in total blood volume. This shift also increases the pressure inside the skull, a condition known as spaceflight-associated neuroocular syndrome, or SANS. SANS is one of the most mysterious and concerning threats to long-term space habitation. The increased intracranial pressure flattens the back of the eyeballs and causes the optic nerves to swell. For many astronauts, this results in permanent changes to their vision, causing significant nearsightedness and even blind spots. On Mars, Where clear vision is essential for navigating a treacherous landscape and operating complex machinery, the slow onset of blindness is a terrifying prospect. We do not yet know if this condition stabilizes or continues to worsen over the years it would take to establish a colony. If the latter is true, the first generation of Martian pioneers might find themselves functionally disabled by the very gravity they once thought would make them feel like superheroes. Even at the cellular level, the lack of gravity disrupts the fundamental processes of life. Recent studies have shown that low gravity can alter gene expression, particularly in the immune system. T cells, the scouts of our immune system, become less effective at signaling an attack when they encounter a pathogen in low-gravity environments. This means that a Martian colonist would not only be dealing with a toxic environment and high radiation, but would be doing so with a compromised immune system. A simple infection that would be easily handled on Earth could become a life-threatening crisis on Mars. Furthermore, the way cells communicate and divide is influenced by the mechanical environment. In low gravity, the cytoskeleton, the internal scaffolding of the cell, becomes disorganized, which can lead to errors in cell division and a higher risk of mutations. We are essentially asking our cells to perform a complex dance in a room where the floor is constantly shifting. The psychological and neurological impact of low gravity is also a major concern. Our inner ear uses tiny crystals called otoliths to sense gravity and help us maintain our balance and orientation. In the reduced gravity of Mars, these sensors provide confusing signals to the brain. This leads to a persistent form of space motion sickness and a lack of proprioception, the sense of where your limbs are in space. For an explorer trying to navigate a narrow ridge or perform delicate repairs on a life support system, this loss of balance and coordination could be fatal. The brain must work overtime to compensate for the conflicting sensory inputs, leading to increased cognitive load and fatigue. The question of reproduction in low gravity is perhaps the final nail in the coffin for the dream of a permanent Martian civilization. We have absolutely no data on whether a human embryo can develop correctly in 38% gravity. Every stage of prenatal development, from the initial division of the zygote to the complex layering of the brain and the hardening of the skeleton, is likely influenced by the gravitational environment. It is entirely possible that a child conceived and born on Mars would suffer from profound developmental deformities, with a skeletal structure too weak to support their weight and a cardiovascular system incapable of handling even a minor physical challenge. If we cannot safely raise the next generation, then Mars is not a new home for humanity. It is merely a high-priced, high-risk research station where the residents are on a slow road to biological obsolescence. As we examine the human body under the influence of Martian gravity, we see a system in decline. We are not adapting to Mars. We are decaying into a form that is less resilient, less capable, and more fragile. The lightness of the red planet is a siren song that masks the systematic dismantling of our hearts, our bones, and our eyes. We are creatures of the earth, bound by its weight and defined by its pull. To leave that pull behind is to lose the very blueprint that keeps us whole. But even as our bodies begin to fail from within, the planet itself has one more weapon in its arsenal, a phenomenon that can turn the entire world into a dark, choking nightmare. In our next chapter, we will look away from the internal decay and up at the horizon, where the great dust storms of Mars are gathering to erase the sun and bury our technology in a red, static-filled grave. The systematic unraveling of the human body in low gravity is a silent, internal process. But Mars also possesses a much louder and more visible weapon that can bring a burgeoning colony to its knees in a matter of days. In the popular imagination, particularly in Hollywood portrayals, Martian dust storms are seen as violent tempests, with winds powerful enough to tip over massive spacecraft or blow explorers across the landscape. While the physics of a thin atmosphere means the wind itself doesn't carry that kind of physical force, the reality of a Martian dust storm is actually far more terrifying than the cinematic version. These are not merely weather events. They are planetary-scale catastrophes that can turn the entire world into a dark, choking, static-filled nightmare for months at a time. On a planet where survival depends entirely on technology and energy, these storms are the ultimate test of endurance, a phenomenon we have come to call the dust storms from hell. To understand why these storms are so dangerous, we must first look at how they form in such a thin atmosphere. Because the Martian air is so sparse, it takes very little energy to move it, but it requires a specific set of circumstances to lift the dust. During the Martian summer in the southern hemisphere, the planet is at its closest point to the Sun in its elliptical orbit. The increased solar radiation heats the ground and the thin layer of air just above it, creating powerful convection currents. These rising plumes of warm air carry fine particles of iron oxide dust high into the atmosphere. On Earth, rain eventually washes dust out of the sky. On Mars, there is no rain. Once the dust is lofted, it stays there, absorbing even more sunlight and heating the surrounding air, which in turn lifts more dust. This creates a feedback loop that can start as a local disturbance and, within weeks, grow into a global dust event that blankets the entire planet in a thick, reddish-brown haze. The most immediate threat posed by a global dust storm is the loss of sunlight. During these events, the opacity, or tau, of the atmosphere increases to the point where 99% of direct sunlight is blocked from reaching the surface. For a colony dependent on solar panels, the most efficient and scalable way to generate power on another planet, this is a death sentence. We have already seen the lethal efficiency of this phenomenon in our robotic explorers. The Opportunity rover, which had survived for nearly 15 years on the Martian surface, was finally silenced in 2018 by a global dust storm that lasted for months. Without sunlight, the rover could not charge its batteries, and without batteries, it could not run the internal heaters necessary to survive the Martian cold. It essentially froze to death in the dark. A human colony would face the same energy death spiral. As the storm rolls in, the power supply vanishes exactly when the need for power is greatest, as the lack of sunlight causes temperatures to plummet even further. Even if a colony were powered by nuclear reactors, the dust itself remains a formidable enemy of machinery. Martian dust is not like the soft, weathered dust we find on Earth. Because there is no liquid water to smooth the edges of the particles, Martian dust is composed of tiny, jagged shards of volcanic rock and glass. These particles are incredibly abrasive and, due to the extreme dryness of the environment, they carry a powerful static charge. This is known as triboelectric charging. As the dust blows across the surface, the particles rub together and build up a massive electrical potential. This sticky dust clings to every surface it touches through electrostatic attraction. It clogs the seals of airlocks, jams the rotating joints of rover wheels, and coats the lenses of cameras and sensors. More dangerously, the static discharge from the dust can fry delicate electronic components, causing unpredictable failures in the very computers that manage a colony's life support. The physical nature of the wind also creates a deceptive danger. Because the Martian atmosphere is only 1% as dense as Earth's, a wind blowing at 100 miles per hour on Mars would feel like a gentle breeze of about 10 miles per hour on Earth. It wouldn't knock you over, but it would be carrying millions of microscopic, razor-sharp particles that act like a slow-motion sandblaster. Over time, this constant scouring can etch the visors of spacesuits, making them opaque and wear down the structural integrity of thin-walled habitats. Every mechanical system on Mars must be designed to be dust-tight, but on a planet where the dust is smaller than a red blood cell and electrically charged, there is no such thing as a perfect seal. The grit eventually finds its way into everything. The psychological impact of these storms is another factor that is often overlooked. Imagine living in a small, pressurized container and suddenly the sun disappears. The sky turns a dark, muddy red, and for the next 3 months, you are living in a state of perpetual twilight or total darkness. The wind howls not with the roar of an earthly storm, but with a high-pitched, eerie whistle as the thin air vibrates against the habitat's hull. You are trapped inside, unable to perform maintenance, unable to explore, and watching your power reserves tick down day by day. This sense of being buried alive by the atmosphere can lead to profound cabin fever, anxiety, and depression among a crew that is already stressed by the high-stakes environment. The isolation of Mars is absolute, but during a global dust storm, that isolation is magnified by the loss of the only visual connection to the outside world. Furthermore, the dust storms interfere with communication. The high concentration of charged particles in the atmosphere can attenuate radio signals, making it difficult to maintain a stable link with Earth or even with rovers and habitats just a few kilometers away. In an emergency, being unable to call for help or coordinate with a rescue team could be the difference between a minor incident and a total loss of the mission. The storms turn the planet into a sensory deprivation chamber, where you are blind, deaf, and cut off from the energy source that keeps you alive. There is also the health risk of the dust itself, which we touched upon in our discussion of toxic soil. During a storm, the concentration of perchlorates and other harmful chemicals in the air inside the airlocks would skyrocket. No matter how many dust brushes or static discharge plates a colony uses, some of that fine, toxic powder will enter the living quarters. The crew would be breathing in these jagged, chemical-laced particles for the duration of the storm and long after. The cumulative damage to the lungs and the endocrine system from a single 3-month global dust event could be enough to shorten the lifespan of an astronaut significantly. As we look at the swirling red clouds of a Martian storm, we see a world that refuses to be tamed. The dust storms from hell are a reminder that Mars is a dynamic, violent planet that does not care about our mission schedules or our technological prowess. It is a world that can change its entire character in a matter of days, shifting from a clear, sunlit desert to a dark, electrified tomb. But even if we could build machines that never jam and power sources that never fail, we would still have to face the most fragile part of any mission, the human mind. In the next part, we will move away from the physical storms of the atmosphere and into the internal storms of the psyche. We will explore the Earth out of view phenomenon and why the psychological isolation of Mars might be the hardest obstacle of all to overcome. The transition from the physical violence of global dust storms to the internal landscape of the human mind brings us to perhaps the most underestimated barrier to Martian colonization: the absolute psychological isolation of being millions of miles away from the only home we have ever known. On Earth, we are connected by a global web of instant communication, familiar environments, and the comforting presence of a biosphere that sustains us without effort. When we send explorers to the International Space Station, or even to the Moon, they remain within the immediate gravitational and psychological halo of Earth. They can look out a window and see the sprawling continents, the shifting clouds, and the vibrant blue of the oceans. But on Mars, that umbilical cord is severed. We are moving from a world of near-Earth exploration into a realm of deep space existence, where the very concept of home becomes a distant, unreachable memory. In this 8th chapter of our investigation, we move from the external storms of the atmosphere to the internal storms of the psyche, exploring the Earth out of view phenomenon and the mental breakdown of total isolation. The most profound psychological shift occurs the moment Earth shrinks from a planet into a mere point of light. This is a phenomenon that researchers call Earth out of view. For every astronaut in history, the sight of the Earth has been a source of immense comfort and perspective, a visual anchor that reminds them of their place in the universe. On the Moon, Earth is a magnificent, glowing orb that hangs in the sky, 4 times larger than the Moon appears to us. But as a traveler moves toward Mars, the Earth slowly fades. By the time they arrive, their homeworld is nothing more than a tiny, bluish-white speck in the Martian twilight, indistinguishable from the other stars to the naked eye. This leads to a sense of cosmic displacement, a deep existential realization that you are no longer a part of the world that birthed you. Psychologists worry that this total detachment could lead to a breakdown in the terrestrial identity, making the crew feel like they are already dead to the world they left behind. Without the visual anchor of Earth, the sense of isolation becomes a physical weight, a feeling of being cast adrift in an infinite, uncaring void. This isolation is compounded by the unrelenting laws of physics, specifically the speed of light. On Earth, we take real-time interaction for granted. On Mars, the distance between planets creates a communication lag that ranges from 3 to 24 minutes one way. This means that a simple hello can take nearly an hour to receive a response. This delay effectively destroys the possibility of a normal conversation. You cannot call your family to celebrate a birthday in real time. You cannot have a quick back and forth with mission control during a crisis. Every interaction is delayed, scripted, and filtered through the vastness of space. This creates a profound sense of social disconnection. Over months and years, the crew would feel less like they are talking to Earth and more like they are sending messages into a time capsule. In an emergency, this lag becomes a source of extreme anxiety. Knowing that help or even advice is 20 minutes away when a life support system is failing can lead to a state of decisional paralysis or overwhelming panic. Furthermore, we must consider the locked room effect of the Martian habitat. Because the environment outside is a lethal vacuum of freezing temperatures and toxic dust, the colonists would be confined to the same small, pressurized modules for the duration of their mission. There is no escape, no stepping out for a walk, and no change of scenery. Every person the explorer sees is someone they have been trapped with for months. History has shown us that even the most highly trained and professional crews suffer from interpersonal friction in confined spaces. On long-term Antarctic research stations or during simulated Mars missions, like Mars 500, small annoyances, the way someone chews, a repetitive story, a minor disagreement over a schedule grow into deep-seated animosities. In a high-stress environment where your life depends on your teammates, the breakdown of social cohesion is a catastrophic risk. If a crew stops trusting one another or begins to self-isolate within the base, the entire mission is jeopardized. This social friction is exacerbated by a phenomenon known as the third quarter phenomenon. Research on crews in extreme, isolated environments shows that morale and performance often peak at the beginning and end of a mission, but crater during the third quarter. This is the period when the novelty of the mission has worn off, the exhaustion has set in, and the end is still too far away to provide motivation. On a multi-year Mars mission, the third quarter could last for over a year. During this time, the risk of clinical depression, anxiety disorders, and even space-induced psychosis increases dramatically. The brain, deprived of the sensory variety it evolved for the smell of rain, the rustle of leaves, the changing of seasons, begins to suffer from a form of sensory starvation. The Martian interior is a world of recycled air, hum of machinery, and sterile plastic. Without the biological noise of Earth, the human mind begins to turn inward, often with destructive results. The psychological burden of constant risk is the final, crushing layer of this isolation. Every breath an astronaut takes on Mars is provided by a machine. Every drop of water is recycled. Every wall is the only thing stopping their blood from boiling. Living in a state of hypervigilance for years at a time takes a massive toll on the nervous system. The chronic stress of knowing that a single mechanical failure or a small human error could lead to an agonizing death for the entire group creates a state of permanent fight or flight. This leads to cortisol spikes, sleep deprivation, and a gradual erosion of the executive functions needed to solve complex problems. We are asking human beings to maintain a state of perfect performance in a world that is constantly trying to kill them, while simultaneously denying them the social and environmental comforts they need to stay sane. Even the concept of home begins to warp. For a colonist, Earth becomes a dream of a world they can never truly return to, especially given the physiological decay we discussed in Part 6. They are trapped in a middle ground, no longer truly of Earth, but unable to ever feel at home on the sterile red plains of Mars. This identity crisis can lead to a loss of purpose. If the mission's goals become unclear, or if the pioneer spirit is broken by the daily grind of survival, the crew may fall into a state of lethargy or nihilism. We often talk about the hardware of a Mars mission, but the wetware, the human brain, is the most fragile component. We have no way to repair a shattered psyche from 40 million miles away. As we look at the psychological landscape of the red planet, we realize that the greatest distance is not measured in miles, but in the silence between people and the void where their home used to be. The isolation of Mars is not just a logistical challenge, it is a fundamental threat to the human soul. We are social, terrestrial animals, and Mars is a world of solitary, alien silence. But even if we could maintain our sanity and our social bonds, we are still faced with the cold, hard reality of the numbers. To get to this point of isolation, we first have to survive the journey and find a way to keep the supplies flowing. In our next chapter, we will leave the mind and look at the logistics nightmare, the brutal reality of why a 7-month journey makes emergency help a fantasy, and why the supply lines to Mars are a thread that is easily broken. The psychological isolation we have explored is not merely a product of the distance in our minds, but a direct reflection of the brutal, uncompromising physics of the solar system. When we dream of Mars, we often treat it as a slightly further version of the Moon, a destination that is always accessible if we just build a big enough rocket. But Mars is not a neighbor. It is a moving target in a vast gravitational clockwork. This brings us to the ninth and perhaps most pragmatic barrier to our survival: the logistics nightmare. While we are used to a world where next-day delivery and instant emergency services are the norm, a mission to Mars exists in a reality where resupply is a matter of years and emergency help is a mathematical impossibility. In this ninth chapter, we move from the internal psyche to the external supply lines, exploring why the 7-month journey and the laws of orbital mechanics turn every Martian mission into a high-stakes gamble with no safety net. To understand the logistics of Mars, one must first confront the tyranny of the Hohmann transfer orbit. Unlike the Moon, which orbits the Earth and is always roughly the same distance away, Mars and Earth orbit the Sun at different speeds and distances. This means that for the vast majority of the time, the two planets are on opposite sides of the solar system, separated by hundreds of millions of miles of void. We cannot simply launch a rocket whenever we are ready. Instead, we must wait for a launch window, a brief period every 26 months, when the planets are aligned in a way that allows a spacecraft to reach Mars with a reasonable amount of fuel. If you miss that window, or if a critical piece of equipment fails on the launch pad, you are stuck on Earth for another 2 years. This launch window is not a suggestion. It is a prison of orbital mechanics that dictates the rhythm of human life on the red planet. Once a crew launches, they enter a 7 to 9 month transit period. During this time, they are more isolated than any human beings in history. On Earth, we are used to the idea of a quick return or an abort to surface. Even on the International Space Station, if a medical emergency occurs, the crew can be back on Earth in a matter of hours. During the Apollo missions, the Moon was only 3 days away. But on a trajectory to Mars, once the engines are cut and the craft is on its coasting path, there is no turning back. There is no enough fuel to stop, turn around, and accelerate back to Earth. The crew is committed to the journey. If a vital life support component breaks on day 30, they must spend the next 6 months fixing it with whatever they have on board, or they will die long before they ever see the red dust of their destination. This leads us to the resupply thread, a logistical connection that is terrifyingly thin. For a colony to survive, it requires a staggering amount of mass. A single human being requires approximately 5 kilograms of consumables, oxygen, water, and food every single day. For a small crew of 6 on a 1,000-day mission, that amounts to 30 tons of supplies just to keep the biological machines running. But the rocket equation presents a cruel mathematical limit. To launch 1 kilogram of supplies to Mars, you need to launch many times that mass in fuel. This creates a snowball effect, where the weight of the food requires more fuel, which requires a larger tank, which requires even more fuel to lift the tank. Every gram is a battle against gravity. This means that a Martian colony can never be stocked like a terrestrial city. It will always be living on the edge of a shortage, dependent on a supply ship that was launched 2 years ago and won't arrive for another 6 months. The medical reality of this distance is particularly grim. In the history of human exploration, we have never had a mission where professional medical help was more than a few days away. On Mars, the crew must be their own surgeons, dentists, and pharmacists. But even the most skilled doctor is limited by their equipment. You cannot fit a full-scale hospital, an MRI machine, or a blood bank into a Martian lander. If an astronaut develops appendicitis, a kidney stone, or a complex fracture, the treatment must be performed in a cramped, low-gravity, sterile, challenged environment with limited supplies. There is no medevac from Mars. A condition that is a routine outpatient procedure on Earth becomes a life-threatening crisis on the red planet. Furthermore, the shelf life of medicines is a major concern. Many common antibiotics and emergency drugs degrade over time, and the constant bombardment of cosmic radiation during the 7-month transit can accelerate this process, rendering the colony's pharmacy useless exactly when it is needed most. The impossibility of resupply also extends to the spare parts problem. A Martian habitat is a machine of immense complexity, with thousands of moving parts, sensors, and seals. On Earth, if a critical valve breaks, you order a new one. On Mars, if you don't have that specific valve in your inventory, you have to manufacture it. This requires the colony to be a self-contained industrial center, equipped with 3D printers, metal lathes, and the raw materials to feed them. But even with advanced manufacturing, some things like high-end microchips or specialized membranes for oxygen scrubbers cannot be made on the surface. If a black swan event occurs, a cascading failure, where multiple redundant systems break at once, the colony has no recourse. They cannot wait for a FedEx from Earth to save them. The history of Arctic and Antarctic exploration is littered with the stories of crews who died because they were missing one vital resource or because their supply ship was delayed by the ice. Mars is the ultimate ice, a barrier of millions of miles that does not care about human desperation. We also have to consider the abort to surface trap. When we talk about colonization, we often imagine a one-way trip. But even the most daring pioneers need a way out if things go wrong. However, the energy required to leave the Martian surface and return to Earth is nearly as great as the energy required to get there in the first place. A return vehicle would need to be a massive rocket in its own right, sitting on the Martian surface, fueled and ready to go. The logistics of maintaining a getaway vehicle in the toxic, freezing, dust-filled environment of Mars for years at a time is an engineering nightmare. If the return ship's seals degrade or its fuel boils off, the crew is effectively stranded. They are not settlers. They are castaways on a desert island where the ocean is a vacuum and the nearest port is 7 months away. Finally, there is the risk of logistical fragility. A colony that depends on Earth for its survival is a colony that is vulnerable to Earth's problems. If a political crisis, an economic collapse, or a global pandemic on Earth halts the space program for even a single launch window, the Martian colony could be doomed. We are talking about a supply chain that is so long and so slow that it cannot respond to changes in real time. This makes Mars a hostage to Earth's stability. For a colony to be truly sustainable, it must achieve total in situ resource utilization, making its own air, fuel, and food from the Martian environment. But as we have seen in previous chapters, the Martian environment is a toxic, freezing void that resists every attempt to tame it. The gap between landing and self-sufficiency is a canyon of logistical risk that we may not be able to bridge. As we look at the immense distance and the cold calculations of orbital mechanics, we realize that the dream of Mars is a dream of absolute self-reliance in a universe that does not allow for mistakes. The logistics nightmare ensures that any human presence on the red planet will be a fragile, high-wire act, where the safety net is millions of miles away and the clock is always ticking. But this leads us to the final, most important question of all. If the radiation is lethal, the air is a vacuum, the soil is poison, the cold is absolute, the gravity is a slow decay, the storms are global, and the logistics are a nightmare, is it all worth it? In our final chapter, we will bring all these threads together to deliver the verdict. We will ask if terraforming is a dream or a delusion, and why, despite our greatest ambitions, we are not Martians just yet. We have traveled through the invisible fire of cosmic radiation, stood in the suffocating silence of a near-vacuum atmosphere, and felt the chilling reality of blood reaching its boiling point at the Armstrong Limit. We have waded through toxic, perchlorate-laden dust, endured temperatures that make Antarctica look like a tropical paradise, and watched as our bones and hearts slowly withered in the weak Martian gravity. We have survived the darkness of global dust storms, the crushing weight of psychological isolation, and the terrifying fragility of a 7-month logistical lifeline. Now, after examining the evidence laid bare across these 9 chapters of investigation, we arrive at the final threshold of our journey. We must face the ultimate question that sits at the intersection of science and hope. Is Mars truly a second home for humanity, or are we chasing a beautiful, rust-colored delusion? This is the verdict. The moment where we reconcile our cinematic dreams with the cold, hard laws of planetary physics. For decades, the concept of terraforming has been presented as the grand solution to all the problems we have discussed. The idea is as seductive as it is ambitious. If Mars is too cold, we will warm it up. If the air is too thin, we will thicken it. If the soil is toxic, we will wash it. Visionaries suggest nuking the polar ice caps to release trapped carbon dioxide, or placing giant mirrors in orbit to reflect sunlight and trigger a runaway greenhouse effect. In theory, this would create a thicker atmosphere, raise the temperature, and allow liquid water to flow once more on the surface. But when we subject these ideas to the scrutiny of modern science, the dream of a green Mars begins to evaporate. A comprehensive study by NASA researchers recently concluded that there simply isn't enough carbon dioxide left on the planet to achieve this. Even if we could somehow vaporize every bit of CO2 trapped in the rocks and the ice, the resulting atmosphere would still be less than 10% of Earth's pressure, not nearly enough to stop our blood from boiling or to provide a breathable environment. Even if we could somehow import the necessary gases from the outer solar system, a task involving the redirection of thousands of icy comets, we would still be fighting a losing battle against the Sun. As we learned in Part 1, Mars lacks a global magnetic field. Without a magnetosphere to act as a shield, any atmosphere we painstakingly build would be slowly but surely stripped away by the solar wind, just as the original Martian atmosphere was billions of years ago. To truly terraform Mars, we would need to perform engineering on a planetary scale that is currently indistinguishable from magic. We would need to restart a dead planetary core or build a colossal artificial magnetic deflector at the Lagrange point between Mars and the Sunday. These are not projects for the next century. These are tasks for a Type 2 civilization, far beyond our current reach, or even our immediate theoretical understanding. Furthermore, we must confront the biological boundary. Even if we could fix the air and the temperature, we are still left with the 38% gravity of Mars. Gravity is the one variable we cannot terraform. As we explored in Part 6, the human body is a product of Earth's specific gravitational pull. We do not know if a human being can live a full, healthy life or successfully raise a child in the lightness of the red planet. We are biological machines tuned to one specific setting, and Mars is a world that operates on a different frequency. To truly live on Mars, we might have to do more than change the planet. We might have to change ourselves. Genetic engineering or cybernetic enhancement might be the only way to create a human that can survive the radiation and low gravity. But at that point, we must ask, are they still human? Or have we created a new species entirely? The ethics of colonization also demand a verdict. We often speak of Mars as a dead world, but we don't know that for certain. Deep beneath the surface, in the pockets of brine or the volcanic vents, microbial life may still cling to existence. If we arrive with our Earth-built microbes, our waste, and our invasive technologies, we risk committing a planetary-scale act of biological vandalism. We might destroy the only other example of life in the universe before we even have the chance to find it. The search for life on Mars is a search for our own origins, and by turning it into a suburban frontier, we may be burning the library before we can read the books. This brings us to the most sobering realization of all, the backup drive argument. Many proponents of Martian colonization argue that we need to become a multi-planetary species to ensure the survival of consciousness in the event of a catastrophe on Earth. But this logic is fundamentally flawed. Even an Earth ravaged by climate change, nuclear war, or an asteroid impact would still be vastly more habitable than Mars is on its best day. Earth has a magnetosphere. It has abundant water. It has a gravity we are built for. And it has a biosphere that is resilient beyond our understanding. If we have the technology and the will to terraform a frozen, toxic vacuum like Mars, then we certainly have the technology and the will to fix the garden we already inhabit. The idea that we can simply move house when we break our current one is a dangerous fantasy that distracts us from the urgent work of planetary stewardship. The verdict of Still Science Lab is not one of defeat, but of profound respect for the complexity of life and the scale of the universe. Mars is not a second home. It is a magnificent, lethal laboratory. It is a place where we should go to learn, to explore, and to push the boundaries of our knowledge, much like we do in the frozen wastes of Antarctica or the depths of our oceans. But the dream of millions of people living in glass domes, walking among Martian forests, is a dream that ignores the brutal reality of our own biology. We are Earthlings. Every atom in our bodies, every spark in our brains, and every beat of our hearts is a tribute to the world that made us. To think we can simply transplant that complexity to a dead rock is a testament to our ambition, but also to our hubris. As we conclude this 10-part investigation, we look at Mars one last time, not as a target for conquest, but as a silent witness to the history of the solar system. It is a world of sublime beauty and terrifying hostility, a place that reminds us how rare and precious our own blue marble truly is. Our future may indeed involve footprints in the red dust, but those footprints will likely be made by scientists and explorers, not by a new civilization of Martians. We are not there yet, and perhaps we were never meant to be. The red planet remains a frontier that challenges our intellect and humbles our spirit, reminding us that while we can reach for the stars, we must always keep our feet firmly on the ground that sustains us. Thank you for joining us on this deep dive into the harsh reality of the red planet. It has been a journey through physics, biology, and the very limits of human endurance. We hope this series has provided you with a clearer perspective on the monumental challenges that lie beyond our atmosphere. If you enjoyed this investigation, be sure to stay tuned for our next exploration into the wonders and warnings of the cosmos. For now, this is Still Science Lab. Good night, stay curious, and we will see you in the next video.